Hello again, Physics 20s. In today's lesson, we are going to take another look at forces, although this time we're going to classify them as non-conservative or conservative. And I'm also going to introduce you to a new physics principle that's called the Work-Energy Theorem. And we're going to use this physics principle to solve systems that are classified as non-isolated. Learning outcome is to describe qualitatively, although we're also going to do this quantitatively, the change in mechanical energy in a system that is not isolated. So let's start off by classifying forces and looking at a conservative force. Conservative forces act internally within a system. So that means the force itself comes from an object that is inside the system that you're actually looking at. Conservative forces do not change the mechanical energy of a system. Whenever we have a mathematical equation, we have that delta symbol. That delta symbol means a change in a specific quantity. So delta EM means the change in your mechanical energy is equal to 0. And just as a quick review, mechanical energy, to calculate it, mechanical energy EM is equal to the sum of the kinetic and potential energy of an object at a particular state in a system. Some examples of some non-conservative forces would be the force of gravity. Well, that comes from within the system because the masses you're looking at are in the system. The restoring spring force, which also comes from the interaction between a spring and a mass inside of a mass spring system. And most of the time, an applied force is actually going to be a non-conservative force, but in the case where you have a rope that's connecting two masses, so the example I'll use is the Atwood's pulley system. So that's the one where we have M1, we have M2, and these two pulleys are suspended, connected to a rope suspended over top of a pulley. Because that rope itself exists within the system, we would also classify that tension within the rope as being a conservative force. Non-conservative forces act externally from the outside of the system. So if someone were to come up and to just kick one of those masses in that Atwood pulley system, then that would be an external force. It comes from the outside. External forces change the mechanical energy of a system. It can either make it go up or it can make it go down depending on the type of force. And we'll look at a couple of examples. So first example is, say that you have an external applied force to a system. Easiest example of this would be you have just a mass, M, and then someone pulls on the mass with an applied force over towards the right. And then if this mass was initially at rest, and if it was on the ground, it would have no mechanical energy. If you apply force to the right and you get the mass to move, then it would have kinetic energy. Therefore, my mechanical energy has gone up due to that increase in kinetic energy. So typically, an external applied force transfers mechanical energy into your system. However, there can be situations where an external applied force can actually take mechanical energy away. So let's think about this from a tug of war perspective. So let's say now that I apply a force on the other end of the mass. We'll call this one FA2. Now, it's a smaller force of magnitude compared to FA. We call that one FA1. And if the mass is moving towards the right, and then someone tries to basically slow the mass down by pulling on it, well, that would cause your kinetic energy to decrease. If your kinetic energy decreases, well, then your mechanical energy is decreasing, and that's a result of that applied force FA2. But usually an applied force puts mechanical energy into the system. The force of friction, however, will always, I said usually, because there's sometimes some weird situations where friction could possibly put mechanical energy into a system, but I think for the most part, or like almost always, in any situation I can think of, the force of friction would result in you losing mechanical energy. You're going to lose mechanical energy in the form of thermal energy, specifically due to the friction between the mass and the surrounding environment. So mechanical energy is going to be lost. I suppose I just put the word usually because it's just difficult to always like use absolute statements like always, because there's, again, usually always some kind of like really weird kind of like outlying situation where it doesn't behave like it should most of the time. But anyways, we're not going to worry about that in Physics 20. What we're interested in today is analyzing a non-isolated system. Non-isolated systems are systems that have non-conservative forces. They can have conservative forces as well, but they do have non-conservative forces. And what do my non-conservative forces do? Well, they change the mechanical energy of the system. Here's an example of this. So this graph is a graph of energy. I'm just going to grab a different felt color. Okay, we have energy as a function of position, or it could be as a function of time if you also want to think about it in terms of time. And we have three different colored lines. We have the red line, which represents the kinetic energy of the object. We have the blue line, which represents potential energy. And then the mechanical energy, well, that's just EK plus EP. So that's both of them put together. Okay, so let's try to describe a system where an object would be moving from like point A to point B, and the graph that we see here would represent this. Okay, so let's say that we start at, I'm going to call this one right here the start. We'll say it's state 1. At state 1, that's my initial position. Let's look what's happening. So at state 1, I have no kinetic energy and I have all potential energy. So this might be like me holding a mass in the air. Okay, just holding it, and I'm about to let go. I'm about to release it from rest. Well, as you release it from rest, your height would decrease. So your gravitational potential energy decreases until you hit the ground at state 2. And as the mass falls, well, it accelerates. It's a free-falling object. Therefore, its kinetic energy is going to go up. However, the mechanical energy from state 1 to state 2 actually decreases. So we can say our mechanical energy, delta EM, is less than 0. Well, why would the mechanical energy decrease? Because of a non-conservative force. What's the non-conservative force here? Well, it'd be air resistance. So you're losing some of your mechanical energy in the system in the form of air resistance, which is a non-conservative force. So this would be an example of a non-isolated system. To deal with systems like this, where we have non-conservative forces and our mechanical energy changes, we are going to apply the physics principle that is called the Work-Energy Theorem. And this is a physics principle that is listed on the data sheet. I want to say it's principle number 3 at the top of my head, but it may not be correct. But it is one of the first few of them. We need an equation, though, from the Work-Energy Theorem. So we're going to derive one. The Work-Energy Theorem tells me that the work done by non-conservative forces, which we'll abbreviate WNC, on a system, will change the mechanical energy of the system. So if we take this statement, we can turn it into a mathematical equation that looks like this. You have WNC is equal to delta EM. I should point out that if you look in the formula sheet, it gives a very, very general equation for this, where it simply just says W is equal to delta E. This isn't very specific, because whenever you see work, you should be questioning work done by what kind of force. And then for delta E, well, what kind of energy is changing? So specifically, the Work-Energy Theorem tells me that if work is being done by non-conservative forces, So that's either usually an applied force, external, or a force of friction. Your mechanical energy is going to change. Now we're going to expand this. Okay, so what are my non-conservative forces? Well, my non-conservative forces could be work done by an applied force, and it could also be the work done by the force of friction. So those are my two big non-conservative forces. Now, in terms of delta EM, well, if we know that EM is EK plus EP, sorry, I don't know why I made a horizontal line there, then delta EM would be equal to delta EK plus delta EP. Okay, so delta EM becomes delta EK plus delta EP. Now we're going to expand the friction term a little bit. So the work done by friction, so again, work is always, if you expand it mathematically, it's the magnitude of the force times the displacement times cosine of the angle between the two. So magnitude of the force of friction times the displacement times cosine of 180. 180 is the angle between the force of friction vector and the displacement vector. And the force of friction is always in direct opposition to the direction that you're moving. Now, cos of 180 is equal to -1. So I then have WA minus FF times D is equal to delta EK plus delta EP. I'm going to bring that negative FFD term over to the other side of the equation. And then I'm going to have WA is equal to delta EK plus delta EP plus FF times D. It turns out, though, that term, FF times D, if you have a force of friction acting on an object over a specific distance, that is going to cause your object or your system to lose thermal energy. So that term, FF times D, force of friction over a certain distance causes my thermal energy to change. And we're going to represent thermal energy with ET. Therefore, I'm going to sub that into the above equation. So I'm going to take this delta ET here, and I'm just going to plug it in right there. And then that's going to tell me that the work done by an applied force is equal to delta EK plus delta EP plus delta ET. And that's the equation that I like to start with whenever I write down the work-energy theorem. So I suppose another way to think of it too is if you had the equation W is equal to delta E. Again, I don't know why it's doing these horizontal lines here. Okay, W is equal to delta E, then W would be WA, work done by an applied force, then delta E would be delta EK plus delta EP plus delta ET. Okay, so let's apply this now. So it says calculate the amount of work needed to change the potential energy of an object from 100 joules to 80.0 joules and the kinetic energy from 10.0 joules to 70.0 joules. Okay. It doesn't really tell me what kind of force is doing the work here. So if it's pretty like, if it's not being very specific about the work being done, I would immediately default to thinking of the work done by an applied force. Okay. I'm also going to do this. I'm going to identify two different states here. So I'm going to say let 1 equal my initial position. And 2 equal my final position. Okay, so now let's write down the work-energy theorem. So the work-energy theorem tells me that WA, this is the starting point that I like to use the equation as. So WA would be equal to delta EK plus delta EP plus delta ET. Now I can get rid of one of these terms immediately because in the problem, it doesn't tell me anything about friction. So I can say delta ET is equal to 0 since the force of friction is equal to 0. Okay, so now let's expand the rest of the equations. We'd have WA is equal to, now a delta quantity is always, you go from your final position to your initial position. So delta EK would be EK2 minus EK1 plus delta EP would be EP2 minus EP1. And now we can just plug numbers into the equation to solve it. So we'd have WA would then be equal to, the kinetic energy at state 2 is 70.0 joules. Subtract the kinetic energy at state 1, which is 10.0 joules, plus the potential energy at state 2 is 80.0 joules. Subtract 100 joules. And then I would have WA is equal to, now it seems like everything here has 3 significant digits. However, if you're just doing addition or subtraction, your significant digits would be based on the lowest number of decimal places. Therefore, that would just turn into, the lowest number of decimal places is nothing. The 100 joules is nothing. Therefore, we just write this answer as being positive 40 joules. Okay, that's a pretty easy one. Okay, second one is going to be a bit more complicated. So this is, a person pulls a 1.2 kilogram box up an inclined plane, a height of 0.850 meters. Okay, so let's sketch a picture to show what's going on here first. So let's draw an inclined plane. And let's say we have a box. So maybe I'll pick a different color for the box. Let's go with purple. And there's a person who is pulling this box up the incline. So we have FA. Now let's say this is position 1 at the bottom of the inclined plane. Then I'm pulling it all the way up to the top. Sorry about that. Let's get rid of this weird horizontal line. Okay. Okay, that's a position 2. And then it tells me the height of the inclined plane. So that's 0.850 meters. And okay, I'm going to try to summarize my information. What I'm going to do is, for the 2 states I have here, so at the bottom of the incline and like at this position much higher, I'm just going to identify a couple pieces of information. So we'll say state 1. At state 1, let's say the reference axis is the ground. It's the lowest point you can go. So your reference axis would be where your height is 0. So I'm going to say that at state 1, your height 1 is 0. And at state 1, it also tells me my speed, which is V1 is 1.00 meters per second. Now let's go to state 2. So at state 2, we know that the height of the incline, so we have H2, is 0.850 meters. And then the speed at the top of the incline is 4.00 meters per second. Now, the reason I do this at state 1 and state 2, identify the height and the speed, is because the height is going to allow me to calculate potential energy, and the speed is going to allow me to calculate kinetic energy. And this is really work you should show when you're doing any kind of problem dealing with you just using the work-energy theorem. You should clarify 2 states of interest, and at the 2 states, you should identify what's the height of that state and also what is the speed at that state. Okay, we want to figure out A, what's the amount of thermal energy that's being produced. Okay, so that's delta ET. Now, to calculate delta ET is equal to the force of friction multiplied by the distance. Problem right now is we don't know like what distance this object has traveled, like from point 1 to point 2. This would be the displacement of the object. So we're going to need to calculate that first. So let's see what we know in terms of, like, we'll assume this is uniform acceleration. So we know that my initial velocity is, and let's say that up the incline is positive. So this is going to be my positive direction. So that's positive 1.00 meters per second. And then my final velocity is positive 4.00 meters per second. That's up at the top. And it tells me how long it takes to do this. That's t. So that'd be equal to 2.00 seconds. And I want to calculate the displacement. Once I get the displacement, then I will be able to determine what the thermal energy change is going to be. All right, so we need to use our uniform acceleration equation that has VI, VF, T, and D in it. So that's the one that tells me that D would be equal to VF plus VI over 2 times T. And then let's just plug the numbers in now and just do this. So this would be VF, which is positive 4.00 meters per second, plus positive 1.00 meters per second. Divide this by 2. Multiply by the time, 2.00 seconds. And then I'm going to get my displacement will be up the incline, positive 5.00 meters. And now we can calculate this thermal energy change, because this thermal energy change, delta ET, again, there's a thermal energy change due to the fact that there is friction over a distance. Okay, so this would be equal to, let's plug the numbers in. So the force of friction is 2.0 newtons times 5.00 meters. And then 2 times 5 is just going to give me 10. So I have 10 joules as my thermal energy change. And that is part A. Now, part B wants me to calculate how much work is done by the applied force on the block. Okay, so now we're going to have to use the full work-energy theorem to do this. So my full work-energy theorem, if I write it out, is WA is equal to delta EK plus delta EP plus delta ET. And we're going to expand this. So this would be WA would be equal to EK2 minus EK1 plus EP2 minus EP1 plus force of friction, or plus delta ET, which we already know. We calculated in the previous parts. I'll just leave it as the delta ET variable. So let's go back here. Plus delta ET. Okay, now we don't know what the kinetic energy or the potential energy is at state 1 or 2, but we can expand this. So we know that WA would be equal to, well, what's kinetic energy equal to? Kinetic energy is 1/2 mv squared. So I'd have 1/2 mv squared, although I'm going to add a subscript 2 here to indicate this is at state 2. Subtract 1/2 mv1 squared plus EP2 is mg H2. So gravitational potential energy is mgh. So we're just going to add the subscript h2 to clarify which state we're at, and then we have minus mgh1, and that's plus delta ET. We could have actually got rid of one of these terms right away. So this is the point of doing the states. The states are going to tell us like what the speed and potential energy is at for our object, for the object is going to be. Okay, so look at this here. At state 1, there is no height. If you have no height, you would have no gravitational potential energy. Oops. So we can just get rid of this term, EP1. Okay, and then now let's just plug numbers in. So we'd have WA would then be equal to 1/2 times the mass, which I believe is 1.20 kilograms, times the speed, V2, which is 4.00 meters per second, all squared, minus 1/2 times 1.20 kilograms times the speed is 1.00 meters per second, all squared, and then plus mgh2, so that'd be 1.20 kilograms times 9.81 meters per second squared times h2. If we go back to our states, we can identify that the height at state 2 is 0.850. And then we just got to add our delta ET term, which is 10 joules. And if we do this, then I believe we should get positive 29 joules of work, which means that even though you do have friction, so friction stealing some mechanical energy away, I'm also exerting an applied force, which is putting mechanical energy in. So at the end of the day, I actually end up, I do positive work, which puts energy into the system. Okay, and this was part B. Now, part C just wants me to determine, okay, what's the magnitude of the applied force? So we can now just write down the definition of work to calculate this. We'd have WA is equal to FA D cosine theta. And in this situation, my displacement is up and to the right. Sorry about that. I might need to recalibrate my drawing tablet. It just seems to be acting really funny today. Okay, up and to the right. And then I also have the force of friction that points in the same direction. That's FF. And then theta would be 0 degrees. They both point in the same direction. Okay, so let's calculate what FA is then. So FA to get FA by itself, just divide both sides of the equation by d cos theta. So you'd have WA over d cosine theta. Let's plug the numbers in. So then we have 29 joules divided by the distance the object moves is 5.0 meters. Again, we calculated that as part of part A in the question. Multiply by cosine of 0 degrees. And then we can get the applied force would be equal to 5.8 newtons I did want to point out that it is possible to actually solve for the applied force using a combination of kinematics and dynamics. So you could actually calculate the acceleration of the object going up the inclined plane. Then you could draw an FBD and an MAD, and you could do the dynamics analysis of an inclined plane. And then you could figure out what the applied force is. But this is actually one advantage of using work and energy, is that it can prevent us from having to do all the annoyance dealing with the vectors for an inclined plane. So on the assignment, which you can complete, called the Work-Energy Theorem, I think you need to ignore just this right here. I think I actually fixed this. This is from before. Okay, complete the assignment called the Work-Energy Theorem. You can do all the questions on it. And yeah, it is possible on that assignment to, again, solve, I believe, everything using kinematics and dynamics, but I wanted to use the work-energy theorem. So an approach similar to what I did in example number 2. I have a bunch of hints listed here, but I believe I also have them posted on the assignment, so you can take a look at that when you complete it. Okay, and I'll talk to you in the next lesson when we deal with conservation of energy.